So first, I would thanks to the organizer to give me an opportunity to talk and to invite me and also our first student from Tokyo Taipei, Tokyo Institute of Technology. And the hospitality is very good. I'm very impressed. Thank you. And so, so let's start my talk. And my talk is on the bounds for the minimal dilatation of pseudo-Anosovs. And maybe some words are not familiar to some students, but the question is very simple. The question is, which surface automorphism is the simplest? Maybe the first answer is identity, but it's not answer, and the second answer is simple densist, and I think is not the good answer. And so our question is, which surface automorphism? It's not trivial and not non-essential. I mean, essential in the surface, and so we have two complexity of the surface automorphism named dilatation and volume. And so my question is, in other words, the first one is, which surface automorphism have a minimal dilatation, and the second one is, which surface automorphism have a minimal volume. And today's my talk plan is in the following. And the first part, I will explain something about surface automorphism, and so the dilatation and entropy and volume would be defined in this part. And in second part, I explain some computer experiment with some theorem about the two complexity. And the third part is maybe the main part, and we can bound the minimal dilatation using the magic so-called magic 3 manifold. And let me see. This time is because after lunch we are very sleepy for some time, so I planned to my talk plan is divided in 3 parts, and if you sleep in somewhere, it's okay, I think. You can continue with in other parts. So yeah, so let's start to my talk. And yes, the second slide is why surface automorphism, and the first reason is very simple. The topological classification of surface has finished long time ago. So there are only sphere and torus and genus 2 surface and genus 3 surface and so on. And but so the next object must be the maps from surface to surface. And the simplest one is from the one surface to itself. And so I want to study surface automorphism. And the second reason is related with 3 manifold. And if you have surface automorphism, we can make 3 manifold, so-called surface bundle, using from surface U product interval, and go top and bottom using the surface automorphism, and we have a new 3 manifold. And there are very strong conjecture which called virtually fibered conjecture by Thurston. And if M is a closed irreducible toroidal 3 manifold with infinite pi1, then M has a finite cover, which is a surface bundle over the circle. What does conjecture mean is, if this conjecture is true, if we understand everything about surface automorphism, we can understand everything about surface bundles. So we almost know everything about all 3 manifolds. So this conjecture is true or not, I don't know, but to understand the surface automorphisms helps to understand 3 manifolds. So that's the second reason for because I study surface automorphisms. And so let's start the first section. Okay, what is surface automorphism? And the surface is simply a two-dimensional manifold, and we use two notation for this talk. D sub n is any punctual disk like this. This is a four-punctual disk. And sigma gn is any punctual surface of genus G. And so this is a sigma 1, once punctured torus. And this is a closed genus 2 surface. And using this notation, I wrote in sigma 2, 0. And this is the surface, and then we can think the map from sigma gn to sigma gn. And easily you can understand composing the two map from this is another surface automorphism. And the all of set is a group with composition. And that group is very big, so we can divide this group by the isotopy, and that group is called mapping class group. So the element of mapping class group is not the map, but the isotopy classes of the map is the element of this mapping class group. And okay, and if we have a map from some space to itself, we can define the topological entropy. And it's not only the surface, but for any space, you can define this topological entropy. And this is maybe the simplest invariant for the map. And the definition is somewhat very complicated, but I should explain this. So first, we take some open cover of X and denoted by C. And first we define the entropy C with F, map F with covering C is this is a number of C and C iterated by F inverse, and C iterated by F minus n, let me see, minus n plus 1. And the number is become very big, and taking a log and divide by n and limit n to go to infinity. And I will explain in the figure maybe here, but that is a definition. And after that, we took the slope of all of the covering C, and we get to this entropy F. It is very complicated, but maybe I can.
What number?
This is a number of the coverings. So let me explain this. So if we have the space X, and space X, we have some open cover of X like this. C is the open cover of X. Is the number of C is in this case 3. X is a white part, and there are 3 open sets which cover X. And then there are maps from X to X, and so this 3 set of C moves like it is not easy to write the exact picture, but some kind of this one moves to this, and this one moves to maybe this, and this one goes to this. And so we have, let me see, maybe we write it F inverse. And so we have new covers on AX in here. And then we write this and this in same time. So there are these three see from here. And let me see. This mark is a common refinement of A and B. So in this figure, the yellow is F inverse C, and the blue one is a C. So common refinement must be like this. So there are so many cover is needed. So many number of open set is in the A and B. So that is entropy. So what entropy is? If we write very simple picture, for example, we start from this square, and the map is the map stretch this to twice in the length and shrink half in the width, and then put half in here. So if the map goes this to, let me see, stretch this like this and fold and put here. The map is from here to here. So if you take once, the refinement is 2, and then let me see. Twice we do this. We have divided by 4, and then we have 8. So we can easily know with from here s minus power of n have 2 power of n power of 2 numbers of open set, and in this case, so this is n times power of 2, and you can take the log, and limit goes to divided by n and take again the limit. The entropy is log 2. So that's a topological entropy, and yeah, okay. Do you think it's okay? Maybe, yeah. Okay, so, and in other words, what this entropy measure is, if this map doesn't mix this surface, the entropy is small, and if the map mix very well on the surface, the entropy goes very big. Okay, so we return to the surface automorphism, and first we say if the simplest is identity, it's not answer. So we want to omit this type of things. So we can define the mapping of phi is periodic if there is some integer and the power of phi is isotropic to identity. It's almost identity, so it's almost a trivial element in the mapping class group. And the second one is like Bain twist. If there are some curves on the surface, and the map, the image of the curves itself So the set C is invariant under the map. So in this case, this map is the mapping class of sigma, but also it's a mapping class of smaller surface with sigma minus that simple closed curves. So in that case, we think it's not essential in sigma, but it's essentially in sigma minus C. So we want to omit this type of things. And there are very useful theorems by Nielsen and Thurston. And non-periodic and irreducible mapping class we want to think about is pseudo-Anosovs. And I didn't explain what is pseudo-Anosovs. It has no meaning, but today we are concentrate on the pseudo-Anosov maps on the surface automorphism, and this is, in other words, is a non-trivial essential mapping class in a mapping class group. And to say about pseudo-Anosovs, first I will explain Anosov map, and I want to write one picture. Anosov map is a map from torus to torus, and let me see. If we have the map 2111 to R2 to R2, here is a two vector 1, 0 and 0, 1. And using this map, this goes to 2, 1. And the other goes to 1, 1 here. Is that okay? Yeah. And it induces the map from torus to torus, because you can divide R2 by Z plus G and you can get torus. So the first torus is here, like this. Let me see, like this. And second torus is more complicated, but you can go here and here and here and here. So the second torus looks like, let me see.メディアンをこうかなlike this. And so we have the map from torus to torus, and this original map has IM value this and this, and IM vector this and this. And what IM value meaning is there is a first IM value around, let me see, 1.6 and 1 around here. This is the first IM vector B. And the image of the B by this map is goes to here and lambda B. It doesn't change the direction, but in IM vector, this vector goes to the parallel to this vector, and only the change is the length. And so, let me see. if I draw the foliation parallel to this line vector, we have a foliation here and here. This foliation is invariant under the action of F because these lines goes to these lines. So this foliation is goes to this foliation, and this is called invariant foliation. And so there are another invariant foliation because there is another vector around here. So sorry, I have only 3 colors, so I should write in white. There is another vector around there, and there is another invariant foliation on the torus. And the difference is in this direction it goes to lambda times, and in this direction it shrinks by lambda inverse. And that is an Anosov map. So what is an Anosov map is in torus there is a 2 invariant foliation like blue and white, and it's invariant under the map. And the width or length is stretched by lambda or shrink by lambda. And that is the definition of Anosov maps. And okay. So I want to do this picture around here. But yeah, okay, I draw in the blackboard. And and there is another point. We call the lambda by the lambda is called dilatation, and in Anosov case it's always degree, the minimal polynomial of the lambda is always degree 2 because it is from the 2 by 2 matrix, and the characteristic polynomial is of degree 2. And so then we can extend this to the higher genus surfaces. And this is a picture, and it may be more complicated, and there are some lamination we can change to the foliation, but to write the picture of foliation is very hard. So that's the reason I use the picture of lamination. And okay, so there are 2 foliation, stable and unstable, and the measure like this. And this is a blue line is stable, and maybe red is unstable. And the point is these foliations are invariant under F, but the measure goes to stretch by lambda and shrink by lambda inverse. And that is the definition of pseudo-Anosov. So it's a direct extension of the original Anosov map to the higher genus. And this stretch factor lambda F is called the dilatation of F. Okay, so, and first I define the map is pseudo-Anosov, and but we can call the mapping class phi is pseudo-Anosov if there is a representative element of F is a pseudo-Anosov. And we define the dilatation of the mapping class of phi as a dilatation of the representative pseudo-Anosov map. And then we have following fact. The degree of minimal polynomial of lambda is bounded by a constant which only depends on the topology of the surface. In torus case, the bound is 2. And if the map, the surface become complicated, the degree becomes bigger, but maybe 3G or 3 or something. It's not so big, and the degree is bounded. So the lambda is algebraic integer of bounded degree, and so we can define minimal because they are algebraic number. We don't need infimum, but we can take the minimal. There exists minimal among the mapping class group, and we want to know what minimal dilatation among the mapping class group. And so that is our main target in today's talk. And let me see. And there are facts. Entropy of the mapping class phi is just equal logarithm of the lambda phi. And I want to explain here with this and these two figure, because in this case, let me see. Okay, in this case, first we have some square here, and it stretches lambda is lambda inverse, and this picture is almost same in here. In this picture, it stretched by twice and shrink by twice, and so it makes coverings the number of the open set like nth power of 2. So if you stretch lambda, there are lambda open cover and lambda square open cover, and there must be nth power of lambda's covering. And so just taking the log, you get the entropy. And that is our reason these two coincide. And so today I use entropy and dilatation confusingly in sometimes. It measures almost the same complexity, but the difference is only a logarithm. And so we can define the minimal entropy as a minimal, the logarithm of the minimal dilatation. Okay, so this is in another word, this is the main target in my talk. And the other invariant is volume, and yeah, I said in the first, but I should explain this. If we have surface automorphism, we can make the mapping torus by this. And from the surface, we product by the interval in this direction, and growing upper side with lower side with surface automorphism. And usually our picture is straight, but I want to see it is it has hyperbolic structure, and my point is here and here are almost the same. And if you make this locally, this and this are grouped by isometry, and we have maybe a hyperbolic manifold, and yeah, it's not explained, but my feeling. I like such kind of picture because this must be hyperbolic. So the straight is some kind of strange for me. And then there are big theorem of Thurston. If phi is pseudo-Anosov, the mapping torus is hyperbolic. So, for any hyperbolic manifold, we can define the volume, and we call the volume of the mapping torus is the volume of the mapping class. So this is these two are our numerical invariants, and so this is the second part of my talk. So we have entropy and hyperbolic volume, and from mapping class, entropy is directly, and it measures the complexity of the map. But to obtain hyperbolic volume, we make mapping torus, and so it's a complexity of 3 manifold. And so we cannot say they are related or not. And so we do some experiment using computer. The easiest case for computing is the braid case. In other words, mapping class of the punctured disk. So in this figure, these are 4 punctured disks, and this braid represents some mapping class. And how to make the mapping torus is very easy, because you are gluing upper side and down lower side, and then add some axis. And so we have this mapping torus using this link. And so we can very easily compute for example, for punctured disk, there are 3 generators, and we made all words up to length 12 by these 3 generators. And for them, I compute the volume using the snappy, and also the trains by Toby Hall, and we can compute the dilatation of blades. And so we do many computation, and we have this picture. For 3 punctured disks, the horizontal side is the volume, and vertical is the entropy. And it's a very good picture, and if it changes to D4, it's like more complicated, and 5 and 6. But you can see there are some lines, and in the below there are no points. So we can easily guess the ratio has some lower bound. And in this picture also there may be an upper bound for this, but sorry, it's not correct, because as in here we have length 2 in here and 3 in here, 4, 5, 6, 7, 8, 9, 10, 11, 12, and it goes to infinity. And the volume is converged because it's some kind of surgery, and the entropy goes to infinity. And so there are no upper bound. But in computer experiment, we can't see, because this goes to infinity as the length goes to infinity. Length is a word length using the Altin generator of blades. I mean, so for example, this part is sigma 1 inverse, sigma 2, sigma 2, sigma 2, sigma 2, sigma 2, and the word length is 1, 2, 3, 4, 5, 6. And this point is correspond a covering of the figure 8 knot. And then we have, so this is I should say in the first, all of this work is joint work with Eiko Kin, and this part is joint work with Professor Satoshi Kojima. And so our theorem is this, and there are some constant only depends on only the topology of sigma, such that for all pseudo-Anosovs satisfy this condition. And in other words, there are lower bounds C1 for the ratio entropy over volume. So I write this line, and theoretically it guarantees there are some lines, and below there are no points. And this theorem is a direct conclusion of the two theorems. And one is very old. This is, let me see. I don't explain anything about Teichmüller space and their metric, but the Bell-Peterson matrix and the Teichmüller matrix can be compared by this equation. And the Bloch's theorem is volume is comparable by the Bell-Peterson matrix of the Teichmüller space. And the entropy is almost by definition related to the Teichmüller distance of 2 points. And so I don't explain any more about using these two theorems, we can get directly this theorem. And so we have only, but we want to see why there are very few points, and we can get the compass inequality for some geometric restrictions if the mapping torus has no closed geodesic of length epsilon, and using epsilon we have some another constant C2, and we have this inequality of compass side. And but we can't explain this. I can't explain this today. Okay, and then Professor Kojima extended this to non-pseudo-Anosov maps using the Gromov norms. And okay, I want to explain this because I didn't understand his theory yet. But so entropy and the volume or Gromov norm is comparable with some mild geometric condition. And so that two complexity is usually very near. It's, I don't know why, but it measures some same complexity in the different way. So, okay, this is the second part of my talk, and we do this experiment, and we see very carefully in the manifold with very small volume and very small entropy, and let me see, it's a 3-punctual disk, 4-punctual disk, and 5-punctual disk, and 6-punctual disk, and we concentrate on the around here. We have this graph, and this is from D3, and this blue one is from D5, and etc. And that is magical things happen, and all of these small dilatations, small volume things are made from the surgery of magic 3 manifold. And first, I want to explain what is a magic manifold. And this is a 3-chain link, and it's arithmetic. And the magic 3 manifold is a complement of the 3-chain link. And today, if I wrote M is always this magic 3 manifold. And why this is magic is because it have so many exceptional delphine, and it was called the magic 3 manifold. And using NIMS-KIAS, sorry, I think in some part I use this NIMS-Q, and in some part I use NIMS over Q for then surgery, then filling of one component of this link. And return to this graph. There are 8 points around here, and this is all points in the volume less than 5.05 something is in there, and this is all magic 3 manifold, but there are many fiber structure, so we have many entropy for one manifold, and these points are all surgery of magic 3 manifold, and this is minimal entropy of 5 braid, and this is a minimal entropy of 3 braids, and this is a minimal entropy of 4 braids. And they are all obtained by magic 3 manifold. And so we think why? And that is a start of our next chapter. And so let me start with this chapter with minimal entropy, and the known fact is it's very difficult to determine the minimal dilatation. And as Professor Hodgson said about the minimal volume, it is also very difficult, and recently they determined the first 10 minimal volume hyperbolic manifold, and it's like, and for 4 punctured sphere and torus and 1 punctured torus, it's very easy to determine the minimal dilatation because the mapping class group can be represented using SL2Z. But the other 2 cases, sigma 05 and sigma 20, is very hard. But recently, Ham and Son, they are all in Korean people. And yeah, I met Son once, and he explained this algorithm, and I'm very impressed. But by the way, these 2 new things, they determine for 5 punctured sphere, the minimal dilatation is this, and this number is the largest root of this polynomial. And what they do is they make this finite state automaton for the mapping class group, and using this, they can prove this is a minimal. And so you think they can extend these to a more complicated surface, but the size of automaton is too much bigger if the surface becomes complicated. So it is a limitation of the size of computation. The result is only sigma 05 and sigma 20. And okay, so we know very few minimal dilatations, and so we can't know exact value, but there are many upper bounds. And to make upper bound is very easy. If you get some automorphism have that dilatation, that bounds the minimal dilatation from above. So there are so many bounds for minimal entropy or dilatation. So, for example, maybe it starts with Pena and Hironaka-Kin and Minakawa, and recent Hironaka's is very sharp. And I will introduce these 2 theorems. RKL is the largest real root of this polynomial. And she made some surface automorphism have dilatation of equal to this RKL for these two, using if Z is 1, 3, 4 modulo 6, she makes some automorphism, the dilatation coincides with this value, and 2, 5 for this. And another thing is asymptotic behavior of the dilatation. If we think genus goes to infinity, we can't know the limit exists or not, so we have to say limit sup. But the Euler characteristic, let me see, sorry, minus negative of Euler characteristic times and minimal entropy is less than this value. And this too is, we think, very sharp bound. And but we can think we may have better bounds because Hironaka's theorems comes from the minus 1/2 surgery from the magic manifold. So if we investigate all of the magic 3 manifold, we may have better bounds for minimal dilatation. So our strategy is very simple. So compute entrophies which comes from the magic 3 manifold, all of the entrophies which comes from the magic 3 manifold. In other words, find all surface automorphism which have whose surface boundary is isomorphic to magic 3 manifold or some defining like this. And so the examples are like this. This is a magic 3 manifold, and maybe you can't see easily, but this link and this link are different from this, but the complement of this link and the complement of this link and the complement of these links are isomorphic. Are you okay? These three are, as a link, these three are different, but the complement is isomorphic. Do you know how to make the isomorphic different link with isomorphic complement? And it's very easy because if you do, let me see, some note with, okay, some link like this, and if you cut here and twist around this and reglue them, the complement is isomorphic, but the link must be changed like this. So if you cut around here and twisting sometimes, and then cut here and twisting sometimes, we can get this link from this link. And that is the reason this and this have two same complement. And there are so many different links, but the complement is magic 3 manifold. And this is a fibration, and this is also fibration of punctual disk. And then these two figures are very similar, and if you forgot this red line, you can get this link. And in other words, if you attach some solid torus in this red part, you can remove this component and you get this new link. So the complement of this link is a defilling of magic 3 manifold. And this is, also have a 3 punctual disk fiber bundle. And so we want to see all of such kind of things. And the remark is all known minimal entropy, that 5 is obtained by this kind of things. And Hironaka's theorem comes from using only this surgery. So we want to know every fibration in the magic 3 manifold, and it's easy because Thurston already compute them. And so how to explain, let me see, to see all fibration in M, we have to define the Thurston norm, and it's easy. So first, Thurston norm is the norm from the second homology to the R, and how to define is first VE. Okay, we represent this homology class by some surfaces. And if the surface is not connected, we define chi minus of S as a negative of Euler characteristic for every component, and sum up all of the component. And then we take the minimal among the representative element for the homology class. And that is a Thurston norm for integral homology class. And then we can extend linearly for rational classes. And there are unique extensions for the real classes. So we can define the Thurston norm for real classes of second homology. And but it will be very complicated. In today's talk, my surface is always a fiber surface, so the genus is always minimal. So you can think this Thurston norm, and today all surfaces are connected, and so today you can think the Thurston norm is just as negative of Euler characteristic. So you can forget these things, and you can think only just as negative of Euler characteristic is the Thurston norm. And using this, there are very big theorem by Thurston, and as a corollary, we can explain every fibration on the magic 3 manifold. Let me see. Okay. So first, we fix the generators of the second homology of magic 3 manifold by this surface beta and this surface gamma and this surface alpha. And so the second homology is like this 3-dimensional space. I should write maybe it's R3. And there is a norm in this space, and we can think the unit ball, the norm is equal to 1. And the norm ball is shapes is this. And instead, I say ball, but actually it's polygon, and it has only 6 faces. And the Thurston theorem says that there is some face called the fiber face, and any lattice point in the cone of this face corresponds to the fibration. And in this case, using this symmetry, all 6 faces are symmetric, and all 6 faces fiber face, and we will concentrate to in this red surface, red fiber face. And okay, in afterward I explain again. From this red surface, red face, you can take any point, any rational point. For example, 1/2, 1/2, and 0. In the layer of this, there are some integral class in this case 1, 1, 0. And this 1, 1, 0 corresponds to some vibration of magic manifold. So in this case, the red one corresponds to this, and the black one corresponds to alpha plus beta. And alpha plus beta is just the surface in this green one, and it has a fiber structure of the magic 3 manifold. And it's a very simple example, but for any rational point in this red phase, there are some vibration. That is a consequence of the Thurston's very strong theorem. And so we can understand all of the vibration in the magic 3 manifold as a point in the second homology classes. Okay. And so we want to compute first the topology of the fiber surface, and it's easy because so let sigma be the point in the second homology, and so almost every second homology we have some surface with surface bundle structure, and we want to compute the topology of the fiber surface. And it's very easy, and the minus negative of Euler characteristic is just A plus B minus C, and the number of puncture of the surface is just this greatest common divisor of A and B plus C and symmetric things. And also we can compute the boundary slope of S. And using the first two, we have the genus is equal to this. And I want to explain the proof, but okay. The first one is because this phase is defined in this equation, and that means the Thurston norm is just this. And second and third, we use the boundary map of the homology from the second homology of M to the first homology of boundary M. We can easily think the we can easily compute the boundary of this surface in here, and that gives us the number of punctures and the boundary slopes. Okay. So, and then we want to compute for every vibration. We want to compute entropy, but the easiest way to compute is to consider entropy function on the whole delta. And there are some theorem by Fried and extended by Matsumoto and then extended by Macmillan. Entropy function from cone of the delta to R has following property, and for integral classes, the entropy, let me see, inverse of entropy is just n times inverse of entropy. And so, using this homogeneous equation, one can extend this entropy to the rational class, and then we can extend to real class. So we have the entropy function on the not only the integral class, but for the real classes. And the point is the entropy is strictly concave function. So it have a unique minimal point in the entire cone delta. And then another thing is Euler characteristic times entropy is constant on the race origin. So you can get every information by the projection to the delta. Let me see. I have some. So sorry, I don't have a picture. So